your introduction. So this is the 5th time that my name has been pronounced correctly in my professional life.
I've got it right.
So thank you very much for that as well. As you can see, this is a sore subject, so I keep track. It's lovely to be here. I think this is my first time in Philadelphia, so thank you for having me. This is a joint work with my co-author and colleague Jingyu Wang. So before we start, allow me to thank both of our universities for allowing me to be here, as well as NSF that funded this work for really a very long time, patiently, and it's only now starting to bear fruit. In fact, this is a talk about a very restrictive version of a fluid flow model that I learned from Richard McLaughlin. I couldn't find a photo of Richard, so he's not here, but I should thank him as well, 20-odd years ago. And this is why I started learning stochastic PDEs 10 years ago, so we know how to answer questions of this type. So this is really an archetypal first answering the kind of questions that I'll come to hopefully at the very end of this talk. Feel free to stop me or interrupt me. Always. This is a technical talk. The PDEs, stochastic PDEs are inherently technical. I'll try to give you a physical picture of what's going on in words. What you see here is a lot of symbolism, so feel free to slow it down or stop. For your convenience, I'll try to have the partial differential equation of choice up here in yellow as often as I can as we go. So this is a random PDE. The randomness in this PDE comes through the forcing term V. And the solution to this PDE will be a solution theta. The terminology comes from other fields. This is not necessarily my choice. Theta will be a function of time, t, and a two-dimensional space variable x comma y in the usual elementary sense. And the equation is a kind of parabolic equation where v dt of the solution is some constant nu, which is just a positive number times the Laplace operator, plus the product of some forcing term v, which depends only on t and x, not on y, times the y derivative of the solution. So this is a model that was introduced. This is actually a very old model from the 1800s. Fluid mechanics specialized to a certain setting, which is a stratified, so-called stratified setting in the work of Andy Maya. And this, so here are some buzzwords which I would like to spend a few minutes telling you about. So this is the model diffusion or turbulent transport of a passive scalar in a random stratified incompressible 2D fluid. So what are these? None of this is mathematics yet, by the way. So I'll spend some time describing the model before we get to mathematics. This is supposed to be a way to entice you to think about stochastic PDEs as I believe, a central subject in modern mathematics. And here's a way that people come to this from outside mathematics a long time ago. So what does this model mean? Well, you have some words here that I need to describe. So to begin with, you have a two-dimensional fluid. We're thinking of this non-rigorous fluid. You have a 2D fluid that has a very special form. So imagine the fluid has no lateral velocity at all. So the fluid is being pushed in one direction, let's say from top to bottom. So think of a fluid tank or an air tank where the fluid is being pushed in one direction. And it has a special structure, the velocity field that describes how the fluid gets pushed at time t at place x comma y. So if you want to know how much velocity you feel, if you stuck your finger in the fluid here at time t, you would feel VTX, no y variable at all. So everybody along this horizontal line feels the same velocity field. Okay.
So y is the direction it's being pushed, and the velocity can't change down that line. Is that right?
It can go up and down, but it can't. So in this model, it's stratified. Which the way you can think of this is that it's relative to the scale of the problem. The push is very odd. Okay. So everybody more or less feels the same velocity.
So it has fixed time.
At different times, you feel different.
Right.
But that's right. That's right. That's very important. So that describes the word stratified here, and maybe 2D velocity field. Incompressible, if you know what that means, this fluid model is incompressible for free. If you don't know what that means, it means it's divergence free in the sense of calculus 2 or 3, depending on what you teach. So it's sort of built into the model. We don't need to worry too much. Random, well, we'll see why random in a moment. Actually, maybe I should say right away, so the velocity field is supposed to satisfy an Euler equation or an Navier-Stokes equation. Nothing to say about that. This isn't a talk about Navier-Stokes. This is a talk about what happens if you put, say, dye into this fluid and are interested in the osmosis or the diffusion of dye in this fluid. So at time 0, you spread according to some initial distribution of dye, and you look at the concentration of dye at time t at spatial point x, that's theta tx. And you're interested in how this dye diffuses because of the turbulent behavior of the fluid. That's supposed to solve this equation. Why is it passive? Intrinsically, we're going to assume that the fact that you introduce the dye does not affect, in turn, the behavior of the fluid. So for example, another example, if you want, we're not computing concentration. Concentration is a scalar quantity you could compute. You could compute some other scalar quantity, for example, temperature. So if you add really, really hot dye to really, really cold fluid, the fact that there's such a huge temperature difference means that your introduction of the hot dye into the cold fluid will in fact change the velocity. You're not allowed to do that in this model. This is not an active model, this is a passive model. And so very early on, people realized that a good way to understand this is to simplify, because of the fact that things are passive, to take the problem and split it and not worry about the behavior of the velocity field as a solution to some complicated equation in this case, but rather model it with randomness. And this is very old. This goes back to Reynolds, 1800s. Half of people in fluid mechanics agree with this, roughly. So now I think I've described everything. The word passive, the word scalar, you're computing a scalar quantity. I'm really thinking of concentration as an example. It helps to have examples. Random, stratified, and incompressible. Okay, and so now that it's random, you have to assume some distributional quantities or properties for this random field. Well, here it is. We're going to assume that it's Gaussian. So the velocity field is presumably caused by lots of small order interactions. Hopefully they're roughly ergodic or independent. They average out. If they do, then some sort of heuristic appeal to some sort of central limit theorem should say velocity field should be Gaussian. So the model is that it's Gaussian. The assumption is that in time, it's delta correlated. So if time were discrete, it is not. We're taking the derivative in time of a continuous variable. But if it were discrete, then this is just a function. The delta function is a bona fide function, which is 1 or 0. It's 1 if t and t prime are the same. It's 0 otherwise. And for Gaussian quantities, 0 covariance or 0 correlation means independent. So it means that if time were discrete, at different times you would see independent noises. If time's not discrete, it's a little more complicated to describe, but it's morally the same thing. And at different places in X, you're just correlated, but built into this is this Kreisman property, introduced by Kreisman in the mid-60s all the way till the 80s and the early 90s, that the velocity field is homogeneous in space. So if you calculate at a given time the correlation between velocity at this point, x comma y, and at this point, x prime comma y, and then shift your x and x prime by a given amount, the same amount, the implicit assumption is that the correlation structure of the noise of the velocity field does not change. So statistically, the fluid looks the same as you scan it horizontally. That's the assumption. This is the model. This is not my model. This is Kreisman model, built on a stratification scheme of mine. To those who know what the following means, a way to get this from classical Gaussian processes, see, the delta function is not a function, so this doesn't really make sense as an honest covariance. What you do is you construct an infinite dimensional varying motion W of t. such that at any given time it's a function of x in a suitable way. So that's a continuous function, so it has a weak derivative, its weak derivative, which is a horrible distribution called white noise. That's VT, VTX. So this is the model. I hope it makes some sense.
So the V, when integrated over little t strips, it becomes a
Brownian motion. Increments of Brownian motion for a fixed x. That's right. And of course, rho has to be an object here, which means that everything I've written before this line that just became red has to make sense. So that forces rho to be a covariant structure of something. And we know from classical works of, I don't know, Herglotz, Bachner, and Schwartz, and Milosh, and these guys, these wonderful people, that means it has to be a positive definite function. On top of this, though, we're going to assume that it's bounded. And from Herglotz-Bachner theory, you know that bounded positive definite functions are in particular uniformly continuous. This is a very important fact about positive definite functions. So rho is going to be bounded. You also might remember or know, yes?
Well, I want to ask you a tangential question. Is the Brownian motion and the white noise harder in 3 dimensions than in 2 dimensions, or is it that part of it relatively the same?
The dimension that I think you might be referring to is the x
Yeah.
on the y.
Yeah.
Here it's Brownian motion in the form. So in x, this is an infinite dimensional Brownian motion, which means that you have w of t, and at any instant t, what you see is a random function, which in the appropriate space moves like a Brownian. So this is infinite dimensional Brownian motion.
Okay.
This is not 2 or 3 dimensional Brownian motion.
But in terms of the t and x, is it essentially the same level of difficulty in different dimensions?
So difficulty in terms of construction?
In terms of studying the model?
Well, it depends on questions that one asks. I mean, we know a lot more about finite dimensional Brownian motions than we do about infinite dimensional. But in terms of construction, I would say it's the same.
Thank you.
Okay, so I think I've explained the meaning of all these words. Just a few other things to relate the model to some of the background problems. The constant nu in front of the Laplacian is called thermal diffusivity. If you know something about fluids, this is inversely proportional to the Reynolds number of the fluid. There's no math on this picture. Even the equation isn't an equation until I can show that it has a solution. Right? This equality signs don't mean all that much amongst fluids. So, but nu is inversely proportional to Reynolds number, and what that really translates to in this industry is that if nu is small, the underlying fluid is more turbulent. Think of this physically, right? It's just more turbulent. On the other hand, there's also a source of randomness here. So what is rho zero? Rho zero is a very important quantity. Rho zero, take t equals t prime and x equals x prime. Covariance of a random variable with itself is its variance. So rho zero.
Asking about nu?
About nu, yes.
So nu is like the dye diffusing out, and we're imagining that diffusion actually is a function of the turbulence, that's why it's diffusing, or just diffusing because everything diffuses?
Well, so that's a question that's part of the answer that I'll have to give. So there's 2 sources that contribute to osmosis here. One is diffusion in the classical sense, which is this and that, and nu tells you how fast that happens.
Right.
But there's an additional source which comes from this force interaction.
Right.
And that's rho zero.
But the nu part, I forgot, you said something that was confusing, and I don't remember what, something about the nu relating to the turbulence, which is...
Right, so if nu is small, this is a more turbulent problem. The diffusion is more turbulent. The diffusion is more slow, but you have more...
I see, the net, everything overall is more turbulent because the diffusion component is smaller. Than
Yes,
the
because the diffusion is small. So nu is 1 over time in the terms of underlying Brownian motion. If you're thinking of some sort of particles, it should be. So it's large time. And rho zero, which is the variance, roughly speaking, the variance of the noise, if you allow me to just ignore this delta function for the time being, is the variance of the noise. So that tells you that as rho zero becomes larger, the noise becomes more fluctuating, and so there's more more turbulence as well. So there's two sources of if you want, chaotic behavior or turbulent behavior. One is mu small, the other is rho zero large, and they're actually separate issues. You can see them separately in the equation. And in fact, much of the literature, there's a huge literature on turbulent diffusion of a passive scalar. What you will find in most of this literature, not all of this is in mathematics, but many different fields are interested in these problems, and much of it is really interested in the case where the ratio of nu to rho zero, that somehow has to do with this thing called the Schmidt number. That ratio is very small, which forces nu and rho zero to be small in the right scale. That's the turbulent regime. So much of this literature is interested in the case where nu is much smaller than rho zero. The thermal diffusivity is much smaller than the variance of the mass. Okay, so that's important for future conversations that we have. Now, for reasons that I hope to convince you are actually mathematically relevant, we're going to generalize this problem. So of course you could generalize things in many ways if you want. There's a reason to do this one. This isn't just for the fun of it. We're going to generalize it by writing the Laplace operator, which is second derivative in x plus second derivative in y, splitting them, and actually adding an additional parameter to the problem. So we're going to actually identify two parameters, call them mu1 and mu2, thermal diffusivity in one direction, that's x, that's mu1, thermal diffusivity in the other direction, and that's y, that's mu2. Now, of course, we could play all sorts of little games here that may seem like trivial generalizations. There's a reason for this that we'll come to later. In fact, what we really want is mu1 equals mu2. So I'm just adding more labels to the symbology for now. But you can see that this doesn't complicate the problem or simplify the problem. It's more or less the same problem. Now, one thing that you might have paid attention to is with my hands, I drew a picture or attempted to of fluid that's moving down. But actually, the fluid that I've described semi-rigorously for you so far does not do that. The fluid that I've described is a mean zero Gaussian process that fluctuates with some variance, which means if you actually simulated it or saw it in real life, it looks like this. It's just sort of wiggling. The velocity has mean zero. On average, it tends to be around zero velocity, so the fluid just wiggles. And this is, of course, not at all physical. So in reality, what people do is, in this world is they do what's called a Raynaud decomposition. This is due to Raynaud from 1800s. They actually assume that the velocity field is not what I said, in fact, but actually there's a mean part, which is mu of tx, which is actually a bona fide velocity field. In the example that I have mentally, it actually is a velocity field that pushes you down, and then you have the fluctuating part on top of that. But what happens is that the ensuing analysis, some of which I hope to show you, doesn't care. It's a matter of whether or not you sit on top of the frame that moves with mu, or you just sit at zero and watch the flow. So we're going to assume that mu is zero. In other words, at the level of techniques, it doesn't matter. You might as well look at just purely fluctuating velocities. And that's what we will do.
Let me do that if the question transports along. Like if I'm looking right here at the diffusion of this dye, but the mu's not zero, and somebody else is sitting on this moving frame, moving away, and they're no longer asking the question, what's happening here?
Well, you can study one from the other by a change of transformation, but I just don't want to describe it. But you can. It really is without loss of shape. Well, you can as long as mu is minor.
I mean, you would have to ask the question of after time t, what's happening, sort of.
Very far out.
Okay.
Yes. That's absolutely right. So of course this is a linear PD. I know it has this random part V, which is not a very friendly object. It's a horrible random distribution. But up to that, it's just a linear PDE. And we know a few things about linear PDE, so this should not be the first talk on the subject. Far from it, in fact. As far as rigorous work in this is concerned, the first existence uniqueness regularity result that I know of comes in the early 90s in the work of Kunita, where he proves what's called a Stratonovich theory for this class of partial differential equations, stochastic partial differential equations. And slightly later, Rozovsky and Krylov, and then Krylov built this huge, wonderful, very deep LP or HP theory of stochastic PDEs, which is really designed to study equations of this type. And they produce an Ito type theory. So I'm not assuming that you know who Stratonovich and Ito are. I'm just telling you that there are two different theories that have been built, both quite rich in their own right, which address equations of this type. One of the things that you need to know, it is important, about stochastic partial differential equations in general, is that unlike the world of PDEs, here there is no canonical way to define a solution locally the way you might in classical PDEs at this time. That's why you can have a Stratonovich theory or an Ito theory that are really different solution theories. They're related, as you'll see, but they're different. And the reason for this is, if you look at the very top in this yellow part, the very important part of this is just a heat equation here, there's nothing to say. The very important part of this equation involves multiplying a very, very rough random distribution by the derivative of the solution. And there isn't a canonical way of multiplying random processes by white noise, for example, which is what this is. The way you multiply this, you view this as a random distribution. You want to define the product of these two distributions, which is, of course, a nasty problem. In this context, one of them is a kind of white noise. And the way you understand this is by integrating this. Now, the question really becomes, what is the meaning of a stochastic integral? There are infinitely many canonical, consistent ways of doing that. Two very important ones that have names are Ito theory and Stratonovich theory. They're different, but they're both consistent canonical integration theories. So when you study stochastic PDEs, and you want to prove, for example, the existence of a solution, a priori you have to have some additional meaning given to the product of two random distributions.
So when imagining this product, I understand how rough V is. Pretty bad, white noise. Derivative, something undifferentiable. But then theta, like we want to be taking the solutions in some class. I have no idea what you're imagining for theta, like what class it should live in.
Well, that's
defining.
ideally it should be at least continuous.
So continuous functions. So that's
That's a
even
big
worse
class.
than a Brownian motion. So it's worse than integral V.
Well, in some sense that can be much worse, but it can't be infinitely worse, as it turns out. But this is an a priori.
But in any case, we might expect. So it's not like an integral of a Brownian motion. It could be worse. It could be sort of like a Brownian motion or worse. So very little of the continuity being assumed that theta.
A priori. Yes. And certainly the derivative could in principle be much worse as a function of t. Yes. And so this is a part of stochastic PDEs which is really different from PDEs. You have to have some agreement ahead of time on what you mean by a product of the random distribution by a random function. And those of you who've kept up with the literature in this world, you know actually Martin Heyer got the Fields Medal for addressing these problems by building regularity structure a few years ago. So this is an area that's of interest to several people in this world. How do you multiply this? And of course, again, the regularity structure theory of Martin Heyer starts with the analog of this problem. What do you mean a priori by a consistent logical statement that says, this is where I would like the distribution product to mean, and then I'll look for a solution. Some technical setbacks. So I presented two works, actually 2 decades of work in those 2 bulleted items. Some technical setbacks here are that when you actually look at the Stratonovich theory that's out there, it assumes that the underlying covariance function, which I called rho, has 6 continuous Helder continuous derivatives. The number 6 is sort of iffy, but the Helder continuity is not. Still, just to tell you why this is a somewhat disappointing condition, the original examples from Crichton from the 60s, rho is not even differentiable at 0. At 0 gives like absolute I of x. This is serious because you all know that the behavior of a positive definite function at 0 is most of the behavior. This is not a subtle technical thing that you do. On the other hand, the Ito theory is disappointing because it has this thing called the coercivity condition. In order for the Ito theory to be able to give you a solution, you have to have a coercivity condition. If you're very, very careful and you work things out, you will see that the coercivity condition becomes the following condition. That mu2, thermal diffusivity in the second direction, is bigger than half times the variance of the noise, which goes exactly in the opposite direction that we would like. We would like mu2, in fact, we would like both mu's to be much smaller than the variance. So that's the turbulent region. And this is preventing you from studying the turbulent region. That's where things are at this stage. And maybe even more importantly, these theories are such that they're really infinite dimensional PDE methods, and so they by themselves have no qualitative information about the solution, even when they do produce solutions. So I haven't told you about the problem that I learned from Richard and Gaussian. I hope to tell you at the end. But that's the sort of problem that can't be studied from resistance regularity methods. Let me actually say a few more things about the Ito solution. So I told you that's disappointing, but in fact there is a way to approach it which gives you some a priori information. So here's a theorem about the Ito solution. If theta 0 is nice, and I'll tell you what nice means later on in this talk. I hope I won't forget. And if this low turbulence condition is met, so if the thermal diffusivity in this direction is bigger than half the variance, that's a disappointing condition, but it's life, as it turns out. You need to assume. Then you have, in the sense of Ito, whatever that means, you have a solution to this partial differential equation. And the solution actually is unique. Moreover, in the y variable, it's C infinity. So in fact, this dd y theta is a proper strong derivative. So this product becomes really an Ito product in the sense of, if you've had mathematical finance backgrounds, you would know it's that. But this is an a priori conclusion of the method. And moreover, let me ignore this second part. Moreover, what this means is, what this implies also, this method that I won't be able to tell you about, what it implies is you can get some qualitative information about the solution. So if things are sufficiently smooth, which means that theta 0 is Helder continuous and nice in the sense that I'll tell you about later, and if the covariance function is Helder continuous, these are very weak assumptions. The absolute value of x is Helder continuous. Then in fact, the solution decays. So that's something that, of course, physically should be obvious. So this is a rigorous statement, but under very mild conditions, the solution actually does decay. As t goes to infinity, you put your finger here, the concentration of the dye here will eventually go away, and there's an asymptotic bound for how fast it goes away. It does not go away any faster than 1 over root t, with probability 1. So that means that every time you simulate the solution, you will see that as time goes to infinity, the solution will decay, not faster than 1 over root t. So these are a priori statements. Again, the handicap is we would like mu2 equal mu1 equals very small. And this condition means, well, if mu2 is very small, then basically rho 0 has to be 0. But if rho 0 is 0, the variance of the noise is 0, the mean of the noise is 0, there's no noise. So actually this goes away in the equation, and you just get a linear heat equation which has no interesting properties worth telling in 2018. In other words, this is a disappointing theorem because it cannot possibly address high turbulence ratio. But it's not a useless theorem. Still, once we're disappointed, and we should be, maybe we'll tackle this a different way. And this is actually an approach taken by many people, including Martin Heiro, to singular partial differential equations of this type. Maybe what we can do is go a different route. So let me just tell you in words, and then I'll show you symbolically. So maybe another way to do this is we just take the noise, which is a horrible distribution, and we smooth it. There are known ways of doing that. I'll show you how to do that. Once you smooth the noise, even though it's random, it's a smooth function. This is a linear PDE. So if instead I do a smooth approximation to the noise, it's just PDE, I just solve it. There's a unique solution. There's nothing to do. And then unsmooth the noise and hope to reproduce the solution to my equation as a limiting procedure. And now I'm bypassing stochastic probability. I don't care about Ito I'm just producing the solution from PDE methods by smoothing arguments. Why not? So let's write it out. So Vtx is a function of t and x. So I want a modifier that's a function of t and x. So start with a smooth approximation to the identity. Any bump function will do. So think of a Gaussian curve in t at times a Gaussian curve in x. That's a very nice bump function. And then take the convolution of that with your random white noise v. That makes sense. Because this phi is not random, this is a very nice distribution in the sense of Wiener. This is a Wiener integral. A very nice classical from the 30s. From Norbert Wiener's work, we just apply that theory to build this integral. A canonical way of doing it. And it's easy to see that when you do this, what you end with is a Gaussian field V epsilon. So it just is a bunch of Gaussian distributed around variables. And as a function of t and x, this is smooth because, of course, you took a pretty rough object and modified it with a super smooth function. So this is smooth. So now, let me say one more thing, which is that in any reasonable way that one could think of, V epsilon goes to V as epsilon goes to 0. Right? You modify the V, and then you undo the smoothing, you get back the original velocity. This is true. Anything that could come into mind that's rational, it's true in that sense. Here's a sense I've written. One way to say it. It doesn't matter. The point is you just take your field, which is a rough object, and you smooth it. Then you solve the PDE for the rough object and take limits, and you can define the solution to your stochastic PDE as that limit, if there is a limit. So this is now a classical PDE. This is a random function, very smooth random function. This is a linear PDE. It's nothing to produce a solution to this. So you do with nothing, you produce a solution. You get theta epsilon. It's unique, it's C infinity, it's a very nice friendly object. Assuming that the initial data is nice, which I have. And so it's true, you do converge. And what you converge to, as epsilon goes to 0, is in fact the Ito solution that I told you that was useless on the previous slide. So it's not so useless. The only difference is you don't go to the Ito solution with nu1 and nu2. You go to the Ito solution with nu1 and nu2 adjusted by half of the variance of the noise. Which is helpful because the Ito theory only made sense when the second thermal diffusivity is bigger than half the variance. And so here, nu2 plus half rho 0 by default is bigger than half rho 0 because nu2 is positive. So this actually is always well defined. This was the previous slide. I could go back to it, but I won't bore you. Okay, so you smooth the noise, you take limits. You don't construct the Ito theory, you construct the Strafanovich theory. In fact, those of you who might know classical stochastic analysis might know there's this thing called the Wang-Zakai theorem, which says you take a stochastic differential equation, you smooth the underlying Brownian motion. Now you have a random ODE. You unsmooth it, you don't get an Ito equation, you get a Strafanovich equation. So what I'm telling you here is that there's a similar infinite dimensional analog of that story, and this is the story. So in terms of buzzwords, the Strafanovich equation just takes the Ito equation and bumps up the second thermal diffusivity by half the variance of this. The nice thing about this Strafanovich theory is that first of all, it's built on physical objects, namely velocity fields that are limits of well-defined velocity fields. This really is an equation of mathematical physics. And so what we have is a limiting object corresponding to that. The other nice thing is it has a solution for all nu1 and nu2, because the second one is always bigger than half rho 0. So I can, in principle, think of nu1 and nu2 going to 0 now.
Two questions. One, did we somehow get out of the Strafanovich theory that requires 6 moments? Did we get
We
out
didn't
of
use that theory.
Right, so we used the Ito theory and got this bumped up thing, which sort of mirrors the Strafanovich theory, but without that nasty assumption. Good.
There are no assumptions except that. Okay, so I'm somewhat lying to you here. The truth is, when it says converges in quotations, rho has to be Hölder continuous, which is a very modest.
Okay, so second question is really philosophical. Is there a case to be made for the fact that when we get this x with 1/2 rho 0, that we really meant to put it there in the first place, that that was the right equation for a physical model?
Well, what you're saying is, I really want the world to be Ito, right? And then this says you have to put everything. But if you don't really want it to be Ito, if you really want it to be Stratonovich, so Stratonovich has the nice property, I know you know this, but I think it's worth saying, that if you apply, say, change of variable formulas, Stratonovich calculus respects that. Right? So if you want a theory that does that, that is physical, if you will, yes, you do need to bump it up. So now you specialize this to mu1 equals mu0. Now we go back to our problem. So this is our PDE. You will go back, and the statement is that the Stratonovich solution to your PDE is the Ito solution to this PDE where you had to bump up the second thermal deficit. There's a unique solution under very, very mild regularity conditions, etc. So I kept saying something about the initial data being nice. How nice should it be? Well, really not very nice at all. It just has to be, so at time 0, where you have the function of x comma y, it doesn't even have to be a function. It just has to be a non-random Borel regular finite measure 1 bar 2. And this is really not that straightforward. This is the initial concentration distribution of the dye in the fluid. So it could be any measure, basically, any measure that you would ever want to fluid. In addition, the proof of this produces what's called a probabilistic solution to this, which I don't want to get into. You can represent the solution to this partial differential equation in terms of the exogenous Wiener measure. So there's a kind of an infinite dimensional integral formulation of this solution, which you can analyze. And so one of the things you get for that is that, I don't know if you remember, but the Ito solution I said never goes to 0 faster than 1 over root t, the decay. Well, actually, for example, if your initial data is a Gaussian cross a Gaussian, so if you have a nice, smooth initial data, that's sharp. Which is interesting because in 2 dimensions, the free heat equation, if you had no forcing, the heat equation would go to 0 at 1 over t. That's the Gaussian current. And so what this is telling you is if you start with a smooth distribution of concentration, then in fact, you get osmosis, you get decay, but it's much slower than diffusion. This answers some of your original questions. That there's stuff going on beyond diffusion. What actually happens is there's site-to-site interaction. That the concentration here actually remembers the concentration before. So the 1 over t is sharp. On the other hand, if you start from this initial data, which is nice, it's a finite Borel regular measure. It's point mass. In other words, if you just take at time 0 a droplet of dye and just put it right here, and watch what happens to that droplet of dye as time goes by, then in fact the exact decay rate is of order 1 over t, not 1 over t. That's diffusion. These are almost sure statements. They happen with probability. So you just drop a dot of y and watch what happens to it. It decays like 1 over time. It just diffuses. There's a constant here which is not diffusion constant. There's an effective diffusivity which I don't want to do. But it is basically diffusion. So it's more or less just forces of osmosis at work. Whereas if you have a smooth distribution of dye at time 0, then in fact it's analogous. It decays slower than diffusion. So you get these as a consequence of some of this approach, which involves writing the solution in terms of addition.
Can I ask if what I'm thinking is correct, or the summary of some of the top of the slide is it seems to be saying 3 things. It's saying this limit exists in the way you said, and then this limit, if you define the stochastic differential equation Ito style, actually solves that. And then it's saying also if you define it in this Stochanovich style, it solves the other thing. So there are 3 things we said at once.
Well, but they're related, so it's all a circle related. And then you get some a priori statements.
And then this other thing that you mentioned that didn't write down is actually a construction of it,
Yes.
which is some exogenous unit process, and then it gives you sort of a formalized construction.
Yes. And that tells you about the sharpness of these decay rates, and much, much more, actually. So let me actually leave some of this and come back to this. So let's keep looking at the case that I mentioned, which is the droplet geometry. At time 0, you just put a drop of dye. And now I'm going to simplify the problem greatly, mainly because this is 86 pages of calculation, and we really ran out of steam, as embarrassing as this may sound. We wanted to solve a certain problem. I haven't yet told you what that problem is that I learned from the class many years ago. So I'm starting to do that. We're only going to do this in the simplest non-trivial case here, which is where the function rho is just identically equal to 1. That's a positive function. Check. That's the function, which is sort of trivial because it means that the underlying noise really is just white noise of time, which trivializes the problem. But it's still, what we're about to do is not entirely trivial. So what happens now is, I mentioned that just because you have droplet geometry, the solution tends to go to 0 like 1 over t. So you put a die right here at 0, 0, and watch how much die you have here at time t. And what I'm telling you is roughly it's like 1 over t. So what does that mean? Well, there are different ways of saying what that means. Here's one way to say it. Look at the set of all times where you have more than k over t concentration here, where k is the constant of your choice. Okay? K is 5. So look at the set of all times. This is a random set, right? You look at the set of all times where there's at least 5 over t concentration of dye. That's a random set. So one question you can ask is it an infinite random set? Is it a very thick random set? Is it a very thin random set? So for large sets, there's this notion of macroscopic dimension. Probably everybody here knows fractal dimension in the usual popular sense, but there's a large-scale version of that, which is very easy to describe. If you have a subset of, say, 0 infinity, which here you have a set of all times, positive times. That's it's a random subset of 0 infinity. So take your set. How large is this set? Well, one way to describe how large it is, you look at how many intervals 0, 1, 1, 2, how many of these intervals intersect your set? Okay? So call that number n sub k sub n. So if you have a bounded set, k sub n is bounded as n goes to infinity. If you have an unbounded set, k sub n goes to infinity. So the question is how fast? Well, if log of this thing over log of n converges to delta, then we say, as n goes to infinity, then we say delta is the fractal dimension of that set. So roughly speaking, if kn behaves like n to the delta, I'm going to say that if you can do that, then delta is the dimension of that set, the fractal dimension of that set, macroscopic fractal dimension. So the macroscopic fractal dimension of bounded sets is 0. If you look at integers, they intersect every one of these. So kn is n, so the macroscopic fractal dimension is 1. If you look at real numbers, it's 1. Okay? It's a little bit different from classical fractal geometry. It's very simple to calculate. In general, if kn behaves like n to the delta, delta is your dimension. So the theorem here is that the macroscopic dimension of the set of times where there's more than k over t die is either 0 or 1. That set is a monofractal in the large asymptotic sense. 1 means it's full in the sense of dimension. It's a one-dimensional set. In this sense, it's everything. 0 means it's basically a bounded set. And the critical k that does the job is some explicit constant. Yes.
Can I go back to what the hypothesis was? There's rho equals 1. Does that mean that it's really v of t, no x dependence at all?
It's just
there's no shearing?
Yes, there's no shearing due to randomness. Yes, that's right. So now we're going to hone in on this 1 over t, or constant over t behavior. So this says, roughly speaking, you should expect decay rates of order 1 over 4 pi mu t. That's what this really means. For most times, you decay like 1 over 4 pi mu t. But it's not for all times. So the question that I was asked was, how can you state, and maybe even prove, that the solution to such equations is multifractal? What does it mean that it's multifractal? How do you state that as a mathematician? How do you prove such a statement? So what I'm about to show you is an answer to all those questions in this very restrictive set. And I'll end here. I think that'll be just about 15 minutes. So it turns out that the right thing to do is to look at decay rates that are slightly faster than 1 over t. So look at the set of all time, same models, most simplified non-trivial case. You put a droplet of dye here, you put your finger at that point and you ask yourself, how much concentration will I see here as time goes by? And you look at the set of times where you see no more than 1 over t times some power of log t. So that's a random set. Now it turns out that set doesn't have interesting geometry. This business of fractal dimensions, what it says is, if intuitively, this is 0 n. N is very large. N is going to go to infinity here. You have some set that traces out some picture. Go far. How far from the blackboard should you go? Go far enough such that 0 n looks like 0 1. And then your set looks like a fractal. And that fractal should have classical fractal dimension delta. Okay? So if you do that here, you see nothing. What you have to do is you have to go e to the n units out, not n units out. So you have to go so far that this looks like e to the minus n. In other words, stuff infinitely far away has to be brought in, jammed in, for you to see geometry. Another way to say that is you take your set of all times where at this point you're seeing decay rate of 1 over t log some power, and you take the log of every point in that set. You shrink the set such that you start to see geometry at infinity when you're far enough such that this looks like 0 1. Okay? Or equivalently, you have to go very far out. And if you do that, that random set has a non-trivial dimension as well, in the same sense. And the dimension is 1 minus 2 delta nu. It's some number, it doesn't matter. This plus sign is in the usual sense. As soon as this number becomes negative, the dimension is 0. So it's the maximum of 1 minus 2 delta nu is 0. Which means that for a certain range of delta, namely delta between 0 and 1 over 2 mu, you see different numbers. And what are those numbers? For different decay rates, you see different dimensions. And this is as close as you'll ever get to a statement that the decay rates form a multifractal on a large scale. And the correct rate for which you see a multifractal is a slight perturbation of the 1 over t diffusive scaling that I mentioned. So actually you see on infinitely many different super diffusive decay rates scales, infinitely many different large scale fractals. So in this very special context, this is the answer to Rich's question that I started to talk about. Allow me to end with one. I have 2 simulations here, but I'll just show you one since we're running out of time. And that's this. So what you're seeing here is, I'm about to lie to you, but then I'll correct my lie. What you're seeing here is theta t00. So you put a droplet of dye here, and you count concentration of dye at this point at time t, and you plot it. T goes from 0 to 10,000. And if you do that, you get nothing. Because it goes to 0 like 1 over t, roughly speaking. So instead, you take the concentration and multiply by t. So that's an order 1 object. And then you take its log. Because you're interested in decay, that thing should go to minus infinity. So you take a log and multiply by minus 1. So now that should be a positive object. And that's what this is, minus log of t, blah, blah, blah. So that's what you're seeing there, both graphs, is minus log of t times the solution at wherever it is that you put the drop as a function of concentration at that place at time t. And time goes from 0, of course I can't let it go to infinity, so I let it go to time 10,000. Okay. The PDF files are quite large, and if you go to 100,000, your most PDF renderers will start to yell at you unless you're very careful. 10,000 is basically infinite. And what you see is so what you want to look for is spikes down. These are unusual decays. Both use the same noise V. The difference is the thermal diffusivity nu here. For the blue line is, I think, 1 or 2 or something like that. For the red line is 14% of that. It's much smaller. And what you see is as nu gets smaller, I should add this here, as nu gets smaller, the range of deltas gets larger, for which this is not zero. Right? Which means you see more and more range of different decay rates on different scales. And you can sort of see that here because as nu gets smaller, here's 1 nu in blue, here's 14% of that in red. The decay rates are much more. And what I'm hoping you will see are different decay rates on a large scale, all of which have different dimensions. I mean, it's very difficult to do this numerically because this is not something you see in numerics, but this is as close as I can come to convince you that there really is a theorem to be said here, and that I've shown you a way to phrase the theorem. Let me just end with saying, because the noise is the same for both solutions, you will see that they spike together. And the blue one goes down, the red one goes down. The noise is forcing both of them to go down, but the diffusion affects how far they decay and to what extent they decay differently. So this is a numerical story, if you will, of the previous theorem in the simplest setting where VTX really is just VT.
To understand that, first of all, the minus log of T gamma, so when they spike down and gamma is spiking up, it's minus log?
Well, it might be plus log, yeah, you're right. Yeah.
So it's spiking down. And then this vertical range is really from 0.99, almost 9 to 1.
It's because log T goes to infinity very slowly.
But in fact,
This should go to 0.
if we ran it long enough, we'd see spikes going down.
All the way to 0 on a different fractal. But it's hard to see it over this much time.
But it's very precise. The fact that these spikes are noticeable and they stay coherent and they happen, it's not, even though it's all within a range of 0.99, it's really there.
And you can explain that from the probabilistic representation of the solution. I don't have enough time to describe it. In fact, another way to say that here are 4 different simulations of the solution for 4 different noises and 4 different nus. Statistically, they all look the same, except if you look on the y-axis, you see they're not all the same. As nu gets smaller, the spikes go much closer to 0. And here I was more patient. Time goes to 10 to the 6th here, which is a little bit larger than what I showed you earlier. And here you see it goes down to 0.1. Again, if you're even more patient, you'll see even greater spikes for smaller units. This is mu equals 10 to the minus 8. Very small, very high Reynolds.
Any other questions?
Yeah, this is going back to, because I really don't know too much of the context, but at some point you mentioned what Martin Herrick did recently, and I want to make sure I understood that from the situation like this. So it sounds like you said that maybe first of all he had to actually define what types of integrals, and is it sort of equals or countervariation integral? Is there some third thing?
Well, he has so the regularity structure theory is a very rich one that goes beyond any given family of equations. I mean, but let me just state it in the context of. Let me just state it in the context for which he got the field.
Okay,
Okay.
that would be useful.
Yes. So this is the KBZ equation. This is its analysis math vector. So if you look at the KBZ equation, it's not quite the same as this. U now is U of Tx. X is one-dimensional. T is time, X is space. And you look for solutions to the following PDE. There could be a nu here, it doesn't matter. And this is just second derivative of X plus U times V. The catch is now V is really space-time wave noise. So it's very rough, and equally rough in T as it is in X. Okay? So for those of you who know, you take a Brownian sheet, WTX, that's a continuous random function of 2 variables. Take a mixed derivative. And T and X, that's V. So that's a horrible distribution. So this is the stochastic heat equation with multiplicative forcing. It has a unique solution, blah, 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 no problem. Now what you want to do is you want to relate this to objects which arise in the analysis of height profiles of certain particle systems. And the right way to do that, and this is a long story that not all of which is regularized even today, the right way to do that is you take a log of the solution. So you would like to say W is log of U. And you ask yourself, what equation does W solve if you do this? So you can do the arithmetic, and you'll see you get an equation like this. Again, very much like this. Let's say this is 1 or something like that. But then what log does is it removes the U here and just gives you a pure additive noise, which is very nice. The cost is it gives you a nonlinear term, which is plus or minus, I don't remember which, the gradient squared, which is a very important point. Now you see what the problem here is that there's no obvious way, so this is added to this equation, there's no obvious way of giving meaning to this. Because, you see, W in X is as rough as V is. It's a horrible distribution. So even defining its derivative is really tough. Defining its square is a serious problem. So it's not even a priori clear, I hope, what this could possibly mean. Except when you write discrete models that are supposed to approximate this object, then it does mean something. And what Martin showed, among many other things, is if you first smooth the noise. So now you have a nonlinear PE, random but nonlinear PE. And take limits, you get nothing. What you have to do is subtract a constant which behaves like constant over log of epsilon. You have to subtract an infinity. And then you go to the solution of the C. In other words, to give meaning to this equation, what you really have to do with epsilon equals 0, this is something that we didn't really know rigorously. You have to subtract a suitable infinity. And so there's this theory of singular stochastic PDEs that comes from this.
When you subtract it and you get some solution on the right, do you also have to create an interpretation for that, or is that like an
Well, interpretation is the sense in which I mentioned, and then there's an integration theory that goes.
And an integration theory that kind of builds in that exactly C all along.
That's right. And then what he proves is that if you do that and just subtract an infinity appropriately, then take the exponential of that, that satisfies the second term. So that's actually canonically the right thing to do.
Okay, thank you.
Does that make sense?
Yeah.
Now, one thing that you need to remember is that this is very important. This is a non-random quantity. Now, what some people do is they build a Gibbs measure from this. So you have to actually multiply the Gibbs measure by e to the minus a non-random quantity. But that's okay once you divide by the partition function. Because everything's non-random, they cancel. So there is, in fact, a canonical Gibbs measure which exists.
This is in the high profile.
It's really, there's really a bona fide Hamiltonian. Yeah, this is the high profile.
Could you come back to the Stratonovich solution and the solution? So for the Stratonovich, the condition on row is more, small, or
Any row will work for starting.
okay.
So the condition for Ito is that the second row has to be bigger than half row 0. Second mu has to be bigger than half row 0. But the Stratonovich always ups it by half row 0, so any new one needs to work for starting.
So Stratonovich is very ordinary.
So in other words, if this were a PDE, it would have to be interpreted as a Stratonovich. This is roughly the thing.